first talks about some tools and resources to designing cost-effective steel bridges. I'm going to do a little bit, then Jeff's going to come in, and then we'll go on to the second presentation. And like he said, I'm Michael Barker. The Short Span Steel Bridge Alliance, I thought we'd talk a little bit about that. It's a group of bridge and buried soil structure industry leaders who have joined together to provide educational information on the design and construction of short span steel bridges. It's made up of all the different stakeholders that are involved with the design and construction of short span steel bridges. And what we mean there is pretty much simple span, although we are going to talk a little bit about some other types of bridges. We deal with buried steel bridges, and we're going to have a talk on that on Thursday. We do rolled beam and plate girders, of course. We have the press brake form tub girders, and we have one of those presentations coming up. And we also look at truss bridges with our members. So what do we do? Well, we do education. Certainly, I'm the director of education for the SSSBA, and we do workshops and webinars and newsletters and things like that. And of course, today is an example of that, teaming with the AGA. We have technical resources with standards and best practices, case studies. I am going to talk about the simple design tool, eSpan 140 today. We also have support for you when you are looking at a project. So this is what I'm going to cover today. I'm going to talk a little bit on a summary of initial and life cycle costs for steel and concrete bridges, because really the alliance was formed back in 2007 to really deal with two issues. One was there's a preconception that concrete is always less expensive in short span bridges. And the second one is concrete bridges are pretty easy to design with tables and manuals and things like that, where a steel design is an original piece of art. And so we've developed eSpan 140, and I'll talk about that. And then with the success of that, we're developing a new design software which actually optimizes the design. I'll talk about that, and then I'll wrap up with some workshops and resources and opportunities. So I only have one slide on this. We looked at county bridges and state bridges and actual costs and bid costs and all those type of things of short span bridges across different states and different regions. NSBA on the bottom left has done it on a national level. We did a big study on life cycle costs out of Pennsylvania. And all of those studies come to the same result or conclusion that typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life. That preconception is a misconception, and that owners should consider both steel and concrete alternatives for their individual bridge projects. And so I show a bunch of stuff here, but you can look at all these reports on the website, shortspansteelbridges.org. So now that we know that owners should consider both steel and concrete, now we have to design them and compare them. And with concrete, that's pretty easy. They have design tables and charts and things like that. It's quick and easy. For steel, like I said, every design was an original piece of art. And that takes time and costs to come up with a design. Now, a lot of states and things like that have standard designs, but in general, it's much more difficult to design. And so when we think about a traditional bridge, we need an 80-foot bridge that maybe we're replacing a bridge. And the owner or the engineer comes up with the service part of this bridge. You know, how long is it going to be? It's going to be 80 foot. And we're going to look at a composite steel girder bridge. We're going to have 2 travel lanes on it with an average daily traffic. We want a 34-foot roadway width. And we like these 1 foot, 3 1/4 inch wide barriers. That's the service part of this bridge. So at the bottom, we see that. That's what the public sees. But what we need is a quick and easy initial design for the bridge superstructure. What's going to hold this up? And so the Short Span Alliance developed what's called eSpan 140, which is standard designs for short span steel bridges, composite bridges. And so it'll do bridge designs from 20 to 140 feet with 4 different girder spacings. And for each of those combinations, it's going to design the steel girders, the shear studs, the stiffeners, the welding and fabrication details, the bearings, and even the concrete deck. So that an engineer or an owner can put that next to that concrete design, and now let's let the market decide which one should be built. And this is a free resource on shortspansteelbridges.org. So I've got this circle here at 80 foot, and it tells us that the C-span is going to give us a rolled beam design. Yep. A plate girder design. Yep. Because they're green there. It's also going to give us a couple manufacturer solutions, which we'll talk about over the next 2 weeks. But we're going to look at the first two, a rolled beam and a homogeneous plate girder design. E-span 140 is very easy to run. You go in and you put in the bridge length, and you put in the number of traffic lanes and how wide you want the roadway width and what your parapet widths and what your overhang that you'd like to use is, and it's going to come out with a couple designs here. Well, it's actually going to have 3 designs, but this one is the rolled shape, lightest weight girder, where it says, hey, 4 girders at 10 foot 6 inch spacing, where we use W36 by 210s and have a couple diaphragms out there, is the lightest weight, and it gives us a weight of, I don't know, 16,800 pounds. It also gives us the camber and all that kind of stuff. For the plate girder recommendation, hey, we can save some weight if we use a plate girder. In fact, that weight goes down 2,500 pounds if we can find a fabricator that can do economical plate girders, because we can transition flanges and that type of thing to save the weight. And it tells us, yeah, we're going to have 16 by 1 flange on top, and the bottom flange is going to transition. We have the same web, and we still have those 20-foot unbraced lengths, and it also gives us that camber diagram. And so just in a matter of minutes for this 80-foot span, we can come up and say, hey, here is a plate girder bridge that will work for that 80-foot span. And I just show the cross section here and the length there. But given that success, because thousands of people have used the E-span 140, we decided that we could even do better than that. We could come up with an Excel-based simple span design software that does not just composite bridges and not just fixed girder spacings and fixed overhangs and things like that, to where it is truly variable to where we can get an optimized design. And so this has been developed, and I'll have a little summary page at the end, but it will do non-composite design and composite design. It'll do up to 4 lanes. We can choose some of the more, the higher strength steels that are coming out from our mills, but it is variable. Like for the bridge layout, you can have a specific bridge length that, you could have 55 feet instead of having to take the 60-foot in E-span. You can have your own roadway width, striped and design lanes, and specific girder spacings that are not multiples of foot and half foot, your own barrier widths and variable overhangs. And there's guidance with this as you're doing that. And of course, this will be a free resource when it comes out on the shortspansteelbridges.org website also. So just some of the power of this thing, the diaphragm is variable along the span. And you can have up to 7 unbraced lengths. And this means we can do skewed bridges, that it's not necessarily symmetrical. That we could have odd unbraced lengths along that span during for a skewed bridge. And in addition to that, we can decide whether we use a wood deck or a corrugated metal deck or a non-composite concrete or a composite concrete, whether that compression flange is braced during construction and whether it's braced in the final state, which of course considers lateral torsional buckling. We can do any decking that's in the AASHTO book, whether it's a wood or a grid, corrugated metal, non-composite concrete, or composite concrete. For composite, it's fully variable with full depth or stay in place forms for a partial depth. You can have haunches, sacrificial surfaces. It'll do the shear connector design. We can add additional dead loads like utilities or whatever. We can have variable bridge railings. And then the steel beams are individually considered in the dead load, so no assumptions has to be made there. And then overall, again, you can have a wearing surface or additional dead loads after the bridge is built. Couple more things, vehicle loading. Of course, it's going to do the Astro HL93 truck, tandem, and lane. But here's one big powerful thing. It'll also do user-defined vehicles. A lot of states have their own state vehicle that every bridge has to be designed to. That even goes into the counties. And we don't have a good way of doing that with some easy software. Now this does it. You can define your own vehicle like a logging truck. You can define its live load factor, whether you want to treat it as a strength 1 or a strength 2 load case. You can either have the lane load with it or not. You can use single or multi-lane distribution factors. And of course, you can change the impact factor. Then it does all the live load distribution factors from Astro for moment and shear. And of course, that's based on the decking. It also does the lever rule and does the rotational analysis, but it also allows you to input your own live load distribution factors if you so choose. And now here's the constraining that it'll do to give you the result that you want. For instance, we can limit the length over depth ratio, and we can say, hey, we don't want to look at anything less than 14 inches or a maximum depth. We don't want anything over a W21 because we don't want to change approaches or we have clearance issues. We know there are W40 and W44s out there, but they're only made by one producer, and so those can be more expensive. So you can have an option on that. Yes, I want to consider them or not. Deflection limits, very important for states, but maybe counties can live with a deflection a little bit larger than L over 800, and so you can define your own deflection limit, and you can put in a % for miscellaneous steel for the diaphragms and things like that. Then, of course, when we design bridges, we can be conservative and use an elastic limit like Astro 610-8, or we can go to the appendix and use some inelastic capacities, and it'll do either. And then, of course, the moment modification factor, CB, is calculated for each unbraced length. But Astro 10 changed that to be the same as AISC, and so that is what is put into here. So it's updated to Astro 10. Likewise for fatigue, it's either a fatigue 1 or a fatigue 2, either infinite life or finite life, and that's based on ADTT, and Astro 10 changed that a little bit, and that's been updated to that. And so what it does is it performs a dead and construction and live load analysis for each unbraced length. It checks the strength 1, strength 2, and constructability design for each unbraced length. It checks service 2 near the center line because that's where the maximum moment is. And it does fatigue at the critical diaphragm location. That might not be at the middle. That could be someplace else. And then the software allows the user to investigate alternatives. For instance, maybe a county has access to some beams that were taken out of service at the state level, and they just want to see, will this work? And they put in this W30 by 116 shown on the left here. And then it gives us what are the performance ratios. And we can see this one doesn't meet the deflection one. In fact, instead of L over 800, it has a deflection of L over 663. Well, the county might say, hey, that's okay for us. We don't mind going over L over 800 a little bit. And we have these beams, and we can use these beams. But also this gives us information to where we might be able to change diaphragm spacing to lighten up the beams. Or we might want to check other beams that are more readily available. Okay, and then so after we do this, and again, this just takes a matter of minutes, the inputs are pretty easy, it gives you a design summary that the engineer needs to look at to verify the design, and it's going to look at all the superstructure design results specific to limit states and unbraced lengths and everything else. It shows dead load deflections for camber. It also gives abutment reaction cases for multi-lane bridges, which can be very helpful when you go to say, okay, now what size abutment do I need? And that's on the bottom left here, where you can say a single lane is lighter, but farther from the center, and a 2-lane is higher, but closer to the center. And so that can be used for that. If it's composite bridge, it'll also give strength and fatigue stud design. So here's where we are. The Excel program has been developed. It has been checked out some. A user manual has been developed with a couple big examples. and is currently under testing and review with some people from the Short Span Steel Bridge Alliance. And we're planning to release this fall at our fall meeting, which is mid-September. And also AGA and SSSBA, us, are doing another webinar series called Building Better Bridges in 2025. And I'm going to be giving an example of this program on September 10th. Okay, so that's what I wanted to show you as far as design. We also have our manufacturers, the members of the Alliance, that will design and fabricate and deliver you a bridge that can be used to replace an existing bridge. It can be used for accelerated bridge construction. You're going to see quite a few examples of this coming up over the next 2 weeks, so I'm not going to talk about them too much here. And so heading towards my summary, here's just a slide that says, hey, there are 5 ways to keep learning about steel bridges. Shortspansteelbridges.org. I really encourage you to go visit that. There is so much information there. You can subscribe to the weekly newsletter, which comes out every Friday morning and just has more or less three hit pieces on what's going on within the short span steel bridge industry. You can find one of our members if you're looking for a bridge or a product for a bridge. We have that eSpan 140. You do have to register, but then you can just start designing bridges. Do it with one that you already have designed and see how it does. See if it'll help you. And of course, we have a support system, number 4 there. And then 5, I've circled this one because this is what I do. Let's schedule a workshop or a webinar. Our director is Dan Snyder. He is on the phone, or he is on the online right now to answer questions and things like that. But here's his contact information. But I want to talk about those workshops a little bit. Now, some of you have probably done at least a couple of these. We do twice a year, we do an online university lecture, part 1, we call it, Steel Bridges from Concept to Delivery. It's 6 lectures as shown on the bottom left here. It's not design, it's an overall industry viewing of the different parts of the industry. And you can read those titles there. It was updated and improved in 2025. We've done 11 workshops. It is a certificate program. Up there on the top right, you do get a certificate of completion to where you can put it on your resume or use it for your PDHs for continuing education. And we have very good reviews on this one. So if you have not done that, certainly encourage you to sign that up, and you can find out about it on the website. We're doing a new one this fall. This is a simple span steel bridge design online workshop. Still, it's going to be a certificate program shown on the top right there, but we're going to go through an 80-foot simple span plate girder design, kind of like that one we just saw in that example using eSpan 140. And you can see the different lectures there. We're going to be using, because ASTRO is really difficult to use directly. And NSBA has come up with something called Navigating Routine Steel Bridge Design. If we just have a simple span bridge, we don't need to be in that complicated ASTRO specification. We can use simpler ways of getting to that design. Here's that one I just mentioned, Building Better Bridges in 2025. We've already done 2 of them on February 19th and April 23rd, and you can see the titles there. We gave out about 500 certificates from that. That's very similar to what you're doing today, where AGA will send you a certificate of attendance. And on that September 10th one, I'm going to be talking about that new software for optimized design. And then on December 10th, we're going to talk about Simple for Dead, Continuous for Live Designs for Optimal Performance. We have one of those next week from the bridge engineer from Missouri DOT. And I'll talk a little bit about that in my second presentation today. We do professional workshops. These are more in-person ones. For instance, on the bottom right there, just last month, we did one in Larimer County, Colorado, where we had the bridge engineers and even the road maintenance people in there talking about resiliency and costs and performance of short span steel bridges. And if you think you're your region is interested in one of these, you can certainly contact us through the website. It's 100% free to the hosting organization. And then several years ago, well, we work a lot with county engineers. We're very involved with NACE, the National Association of County Engineers, and a lot of counties build their own bridges, which means they save a lot of money, which means they can build more bridges. And if anybody's strapped for money, it's counties. And so we developed a 6-part education program to talk about counties building their own bridges, developing their own workforce and building their own bridges. And we have this one, and we've given it a couple times to NACE and a couple other spots. But so you'll get a copy of this, and I put a sample video down at the bottom left for you to explore this a little bit more. And so this is my last slide. We're back to this. I encourage you to to go to shortspansteelbridges.org and see what it can do for you. And with that, Jeff, I'm going to turn it over to you, and you can start your presentation.
All right, thank you. 1 second. Let me just get it up here. Let's see. All right. Well, thank you, Dr. Barker. That was a great presentation. Lots of good questions too. I just wanted to kind of come in and tell you a little bit about the AGA, the American Galvanizers Association, and then also just all the resources and tools we have for, of course, designing effective and cost-effective bridges that will last a very long time and, of course, sustainable and low maintenance. Here's just a little bit about the AGA. We represent over 172 hot dip galvanizing plants in North America, 76 companies. We provide technical expertise in everything from design, inspection, specification of galvanized steel, marketing support for our members, of course. We put on these webinars. We provide continuing education free of charge for AIA and RCEP, so architects and engineers. And then, we're just a free resource for everybody, for all the North American specifiers out there. We provide guidance on specifying hot dip galvanizing, design, installation, inspection, pretty much all of it. So please use us as a resource, when specifying your next project. All right, so I'll go over just a couple of our tools and resources. This is just the tip of the iceberg. Obviously we have a ton of stuff for you guys. The AGA has been established since 1934. So we've been collecting data, real world data from around the world. So all of our stuff is very scientific and very organic around, collecting data over almost 100 years now. All right, so first and foremost is just our website. It is absolutely a powerful tool, chock filled. We'll go over the real resources it has up top, Galv Locator, a project gallery, our publication seminars, and then our cost calculator, which is great because you can put in your project parameters and then it'll spit out everything that you need to know comparative to other coding systems. Dr. Galv Knowledge Base. This is more than 400 short Q&A articles. So it's just questions and answers from, the 100 years we've been around. And they're organized by category. It's very visibly searchable. It's anything from the hot dip galvanizing process all the way to environmental health, safety, and welfare, sustainable aspects, recycling. It is tailored towards galvanizers, but it's also, we have a section tailored towards specifiers that gives more information about designing for galvanizing, working with galvanized steel, that sort of thing. Here's just a few of our really popular resources that you can download for free, and you can also order hard copies as well for very inexpensive. But of course, we have our knowledge base, but then we have our design considerations, both our design guide and our design poster. What's great about the design poster is, it's just a poster you can hang on your wall in your office, somewhere in the break room, but it just gives common design and fabrication details for galvanizing and, vent and drain holes, lifting points, asymmetrical designs, that sort of thing. And then it goes into full detail within the design guide. It's 30 pages long, I believe, and glossary indexed and everything. So easy to find information, including diagrams, charts, some examples and stuff like that. So really good, handy stuff to have. And once again, this is all from our website. You can download for free. You can also put in an order for hard copies. We launched a new website a few years back, kind of in line with the BIL, the Bipartisan Infrastructure Law Act, that actually passed a few years back, but now we're actually kind of seeing the money starting with projects and stuff. So we developed a markets.galvanize.org website that just highlights all the different markets that hot dip galvanizing can be used in within the infrastructure. All the way from transportation, highway or bridge, of course, rail, all the way into, solar, renewable energies and stuff like that. And when you click on these, it kind of gives a demonstration of these little graphics of everything that's blue is what could be the components that could be galvanized. And then when you click on that, it'll drill in deeper. So it kind of gives you a perspective of how much galvanized steel can be used on all these projects. All right, our zinc coating life predictor. This is probably one of our most sought after resources, just because everybody wants to know, how long does galvanized steel last in my environment or in the environment I'm building in. And what we've developed is a zinc coating life predictor, and this once again is off of almost 100 years of real world data. It is not developed off of spray testing, which is critical because salt spray testing does not allow the zinc patina to develop. And the zinc patina, the zinc hydroxides and zinc carbonate develop on the surface and really lengthen the life of that galvanized steel, giving it that 70, 100-year design life. So this is all of real world data. You put in your project parameters and everything like that. It's developed also in conjunction with Dr. Gregory Zhang, if anybody's noticed or him in the corrosion world, very big, famous name. So when you put in all your project parameters, it'll give you something like this, time to first maintenance chart. Now, time to first maintenance, it's important to define as only 5% rusting of the steel surface. So very minimal rusting of the steel surface. Now, ASTM A123 requires at least 3.9 mils on any structural piece of steel of zinc. Now, typically, I know from pretty much all galvanizers, it's going to be above that, obviously, but more like 5, even 6. But let's just say, for sake of argument, we have 4 mils of zinc on our piece, and we're building in an industrial environment, a pretty harsh climate. We're still looking about 75 years before 5% rusting of the steel surface. We could get out there and see that, there might not be 5% rust, or it's past its design life. It might only be for 70 or 75 years. So this kind of gives you an idea of how long galvanized steel lasts in some of the harshest climates. Feel free to try it again. It is just zclp.galvanize.org. Also, we have it linked on our homepage. Here's some other interesting resources and helpful resources in obviously bridge construction. You're dealing with a lot of soils, so we do get a lot of soil questions. So we've developed these soil charts, once again, off of real world data, and these actually estimate the full service life of galvanized steel when you know certain elements of that soil. So once you test the soil for chlorides, moisture, and pH level, then you can figure out which chart you're working on. So let's say we're working low chlorides, high pH, we'll be on chart 3. Anything green is more favorable, anything is red is less favorable. Always a good estimate for 4 mils of zinc on a piece. Still, over 60, 70 years, So anyway, these are all free. You can download this as a PDF, kind of have this as a handy And this once again, it's not time to first maintenance. This is complete service life. So service life is defined as the time to necessary part replacement. So total zinc consumption plus 25%, just FYI. All these, when you do get a PDF of this presentation, all these do have links to all these resources for you guys as well. Our life cycle cost calculator is probably our most powerful tool. It just shows the life cycle cost savings throughout the life of the project. So this is including maintenance cycles, time of value. So we did interest and inflation as well. And oftentimes when you run these life cycle cost calculations, you'll see that hot dip galvanizing's initial cost is its entire life cycle cost, just because it lasts so long in these environments. It doesn't require touch up and maintenance like paint or other coating systems would. And then our life cycle cost calculator is all to ASTM A1068. We'll kind of show a little example of all the inputs that you can have. The square footage, tonnage, what's the expected use, the design life in years, complexity of the structure, typical sizes and shapes usually, all the way up to light trusses, light structural, medium. And then you pick your environment and, going off of all the real world data, it prints you off a nice little life cycle cost comparison. And it has a really helpful, you can download it as a PDF. So it's a, kind of helpful tool, comparison tool when picking coding systems. All right, we get this question sometimes about, well, I'm building a big bridge and I have pieces that are larger than the galvanizing kettle. What can I do? Now, many kettles are up to 60 feet now. Some of the newer ones, most are right around 40 feet. But if your piece is bigger than that, they can do a progressive dip, which is pretty much dipping one side and then flipping around, dipping the other side. There are a lot of progressive dip resources for this. So we do have charts. We also have a galvanizer locator, and it sorts by kettle size. So you can look for the galvanizers in your area with the larger kettles. And we also have a progressive dip calculator. So if you're really worried about a piece fitting in there, you can use our calculator to make sure it will. And then, of course, just consult with your galvanizer. They want to know what the project is that you're working on, and they can fit pretty much anything you can imagine into one of those kettles. I've seen it done before. So, if you're working with oversized pieces, we have resources for you. Just a couple more. It kind of goes into depth on progressive dipping. We've heard a lot of misnomers on it's been called double dipping, or everyone has these expectations kind of from past projects, whatever. But if you think about it, you're taking a piece of steel, you're heating one part of the steel up to 830 degrees, while the other piece of steel is ambient temperature. So of course you're going to release all the stresses within the steel, but also it's you just have to manage the expectations. The overlap line, you'll see these overlap lines in that bottom picture of where it essentially got double dipped, but those will eventually fade out over time. I've even seen them fade out over 6 months. It's just the uneven heating, and then it is susceptible more to warpage and distortion. But that's once again why you have a talk with your galvanizer. And then they have certain mitigations that they can help with that as well. All right, we get inspection of galvanized steel products questions all the time. So we have a wealth of information on inspection. These are just all steel is always inspected to verify conformance with ASTM specifications, ASHTO if you're working international, ISO, some other standardizing organizations out there. Typically, it's a visual inspection with the naked eye. Coating thickness can be checked by a magnetic thickness gauge. We have a publication on inspection, gives you a clear visual guide to it. We have a whole online inspection course. which you get to take a test, you get emailed a certificate, and then your name is on our inspection course list. And if you wanted to, you could even reach out for a inspection course hard hat sticker. We also have a free inspection app at galvanizeit.org/mobile. It gives clear visual guide to surface conditions of galvanized steel, but once you download the app, it doesn't require service. So if you're out in the job site in the boonies and you don't have service, you can still use our full app. Once again, it's free of charge. You can check it out there at galvanizeit.org/mobile. All right, here's a few of our publications. We have more than 40 publications available, and also white papers, case studies. We're just chock full of information over here at the AGA. But here are some of I just put a few of our popular ones. We have bridge specification publications, hot dip galvanizing steel bridges, a practical design guide. Reinforcing steel, galvanized reinforcing steel is becoming more and more popular because it actually protects the concrete from outgassing, sprawling, cracking, that sort of thing. We offer a full course on galvanized rebar as well, and a full course on duplex systems. That's paint or powder coat over galvanized steel. It's becoming more popular, just added corrosion protection, but then also the galvanized steel will help protect the paint and powder coat from peeling, cracking, bubbling, and actually prolong the maintenance cycles of the paint and powder coat as well. Like I mentioned, the inspection of galvanized steel products, and then galvanized hot dip galvanizing for sustainable design, which is great. It goes over all the sustainable aspects, the highly recycled content of galvanized steel. And then our galvanized seminars, we do these webinars similar to the one today, 2 to 4 a month. We always have live Q&A. We'll always try to get a couple of our colleagues on the line and be able to answer questions live. Find out all of it at galvanizeit.org/webinar. We constantly update that page with all of our new webinars, our featured ones, so feel free to bookmark that page and come back to it. We do have on-demand courses as well. 12 courses available. Our popular ones are designing for hot dip galvanizing, reinforcing steel, and then duplex system. All self-taught. So you just go through a course and take a short test at the end and get a certificate of attendance. And of course, we offer lunch and learns all across the U.S. and Canada. We have our members all over the place. So if you want to lunch and learn, submit a form, and then we can get a galvanizer out there. Sometimes they even offer plant tours as well. We have a plant tour now that's accredited by AIA and RCEP, so you can go visit a galvanizer and get a certificate of attendance for it. So pretty nifty. All right, well, that kind of brings me to the end of my presentation, just because it was on solely on the resources of galvanized steel. So if you would like, Dr. Michael Barker, I could go ahead and kick it back to you.
All right, you see my slides, Jeff?
Let me stop my share here. All right, there you go. Yep, you're good.
I think I got you. Okay, thank you for that, Jeff. So I'm coming back, and with me is joining me is Gary Wisch, who works with DeLong's Inc., a fabricator out of Jefferson City, Missouri. We're going to talk about Bridges of Franklin County, which is kind of course, a cute little play on Bridges of Madison County with Meryl Streep and Clint Eastwood, but this is the Missouri version. So I mentioned it a little bit when I talked before. Over the years, that preconception that concrete is always less expensive than steel for simple span bridges was prevalent across the whole country. Many times steel was not even considered for short span bridges. Owners were paying more than they needed to for bridges. And we don't like that unwarranted lack of competition for any industry. And Missouri was one of these. Now, Missouri is a very good bridge state. I'm going to talk about them a little bit later also. But Missouri, like many states, assumed concrete was less expensive than steel for short span bridges. In fact, in some of their guidelines for rural design, they had that if you're planning to build a steel bridge, assume $120 per square foot. And if it's a pre-stressed concrete one, $95. Well, no wonder we weren't building very many steel bridges with concrete being 20% less expensive or steel being 26% more expensive. So if we look at Missouri bridge construction for over 10 years between 09 and 2018, they built 378 typical, now I do need to say typical concrete bridges. And they only built 16 typical steel bridges, where 15 of them were plate girders, and only one of them was a wide flange bridge. And if you do the math, that comes out to only 4% of their typical bridges turned out to be steel. Why? Because they assumed steel was $120 per square foot, concrete was 95. But in 2018, DeLong's Gary and the SSSBA, me, and MoDOT, one of the people, Brian Hartnagel, who you'll hear from next week, worked together to study steel and concrete costs for these typical bridges in Missouri. And after that study, 2 workshops were delivered, one in Kansas City and one in St. Louis in 2018, that discussed these results that were presented to MoDOT people and consultants and contractors. And what that message was no, results showed that steel and concrete bridges are competitive for short spans. And so that problem was solved. Missouri came in right away that December of that year and said, hey, we're going to remove that cost guidance and we are going to compete steel bridges equally with concrete bridges. And to the right there and to the little link to the bottom left, you see a little bulletin type report from DeLong's on their website of kind of a summary of that study if you are interested. So what happened? Now that MoDOT said, okay, let's not assume concrete was less expensive and let's compete steel and concrete. What happened? Well, a bridge came up pretty soon right after that in Scott County where they were replacing a bridge. Of course, they were making it a little bit longer and a little bit wider for hydraulic opening and for, modern lane design. And it was a 45-foot simple span with a 26 8-inch width. And of course, we're going to look at composite rolled shape bridge, and a pre-stressed I-beam bridge. And that's what they did. And it went out to bid, and there were 8 bids from general contractors, 4 for the steel solution and 4 for the concrete solution. And wow, what happened? The low bid was steel, where before this, they would have just assumed concrete was less expensive. And not only was the low bid steel, but it was galvanized beams, which is kind of the Cadillac of corrosion protection systems. And then if we look at the bids, the closest concrete bid was $290,000 more than the steel bid. Now, this is a county bridge, yes. $290,000 is a lot of money for a county, and they saved that because they competed steel and concrete, and steel came in and won that bid. So as another example, let's look at a large project. This is a large design build bridge bundling project. Now, Dr. Hartnagel is going to talk about this on the 17th, but I just want to talk a little bit about it here. Missouri is probably the leading state, if not the leading state, one of them, for design bid bridge bundling projects. They have, I don't know how many at this time, 28, 30, something like that. And this is just one of them, fixing access to rural Missouri or farm, where they replaced 31 bridges under a contract, and they got federal funding and all that kind of stuff. And it goes out to a design build team, and we can see 3 teams bid on this one. Now, Missouri does it a little different than some others. They don't say, give me a price for doing this. They say, this is how much money we have. Tell us what you can do, and we're gonna pick the best value for that fixed budget. And they look, of course, at square footage and number of bridges and things like that. But they also look at quality and longevity, some of the more qualitative things of bridges. And they look at how it is constructed and how it affects public travel and things like that. And so we see 3 teams bid on this, Team 1, Team 2, Team 3. 1 and 2 were primarily concrete bridges. Team 3 was primarily steel. From the design build team of Lehman Construction out of California, Missouri, Wilson and Company out of Kansas City, and DeLong's out of Jefferson City. And you can see they won that bid. Steel bridges. How did they win this bid? Well, the economy of steel bridges was certainly a big part of that. And one of the key factors there was in the green there, it says innovative, simple for dead load, continuous for live load, or SDCL designs. And we saved a whole presentation from Dr. Hartnagel on that for next a week from Thursday, and we're looking forward to that. But also performance of steel bridges. Those galvanized beams rated really high compared to a concrete structure. And they had full depth cast in place decks, which MoDOT graded as higher than the partial depth decks of the concrete structures. And so they took the highest score for those first two categories. And in the third category, they took the second highest score because equipment and ease of construction for steel bridges is pretty easy compared to the heavier equipment required for concrete bridges. So here's a case where they competed and steel bridges won. So now let's get to the bridges of Franklin County. So there are 5 bridges in Franklin County to be replaced between 2023 and 2025. Almost all of them are in place, I believe, not all of them. And you see at the top the name of the bridge. Then the next row is the type of bridge, and we see steel won 4 out of 5 bids. And that's what we like to see. Well, we do. Today, we like to see steel win the majority of them, but we do like to see concrete win some of them. We want that healthy competition between concrete and steel because that's going to give us a better product at a better price. Then the next row is the low bid, and we can see what that was for those. And then the next line is the lowest other material. So for instance, for that very first one, Hendricks Road, the steel bridge was $549,202, and the lowest concrete was $748,163, and then just a percentage beyond that. And then below that, for the rest of that table, is how many bids there were and in what order did they come in. Okay, so we see that table and we see steel did well when it can compete. In fact, we can see in the red up in the table, the ones that went steel, the savings over the concrete options. Then down at the middle at the bottom says, hey, overall, steel saved $280,000 for this county because they bid and didn't just assume concrete was going to be less expensive. Now, the 2 I've circled there or ovalized there are bridges that were built or designed and then fabricated by DeLong's Inc. And I'm going to let Gary talk about those 2 bridges as we go through the different parts of those.
Okay. Is my audio working all right, Michael?
Yep, you're sounding good.
Okay, very good. So I'm Gary Wisch, and at the time these were fabricated, I was the chief engineer here at DeLong's. I've since moved into a part-time role and semi-retired, but still somewhat familiar with these projects. So when we look at Hendricks Road and the other one that we fabricated, Lockhart Road, what's there to like about these bridges from a fabricator standpoint? What made them desirable for us? Well, obviously, the first thing is the superstructure is steel beams and not concrete beams. So that's the obvious thing. But then let's look at some other reasons why they were affordable, relatively inexpensive to fabricate. Hendricks Road, on each of the beams on the Hendricks Road project weighed less than 5,000 pounds. So we can lift these with lighter cranes. The bridge was so small and lightweight that we could ship the entire bridge on a single truckload. And we have 3 fabrication areas in our shop. And these pieces were light enough that we could use them to kind of fill in a schedule in any of the 3 fabrication areas. Can we go to the next one? So the next thing that we like about it is it's made with weathering steel. It doesn't require any coating. Now, we blast clean these beams to make sure that they would weather evenly. So a quick run through our wheelabrator to get an SP6 commercial blast finished, and these beams were finished. Can we go to is that the last Hendricks Road, Michael? There we go. We like that the fabrication is simple. There are 4 bearing stiffeners on each of the beams, and there are diaphragm connection plates. There are shear studs that are shop welded to the top flange. You can't see this in the picture, but that's where we get the composite action between the beam and the slab. All right, let's move to Lockhart.
Oh, you still have some more pictures here.
Oh, I didn't
Talking about
realize
the
that.
simple details and the bolted in, just lift it in
Well,
place and bolted in diaphragms.
well,
And
we're going to get to that in just a little bit. I didn't
okay,
realize
here's Lockhart.
there we go. So the Lockhart Road Bridge is similar to Hendricks. The roadway width is 28 feet compared to 24 on Hendricks. So the engineer chose to use 5 beam lines wide compared to 4 on the previous bridge. This one is on a 20-degree skew where the previous bridge wasn't skewed at all. But to be quite honest, from a fabrication standpoint, that really doesn't make the bridge any more complex. Now let's go to the next one. The rail is similar to the previous bridge. Now we didn't supply the rail, but we could have. But it's just another example of where the engineer and the owner went with a clean and easy to fabricate detail. And even though this bridge is skewed, the diaphragms are perpendicular to the beams as opposed to being skewed to be parallel to match the diaphragms, and that makes it easier for us to fabricate when we're square to the beams instead of with the roadway. Both of the bridges had alternates listed for the diaphragm connection plates, and I don't know if yeah, there should be. If you go on a little bit further, Michael, there should be a detail of that.
Yeah, there should be. I don't know what happened here.
I don't know either, but I'll talk about it while you're trying to find it. We chose a welded diaphragm connection plate on the first bridge, Hendricks Road, because we're more familiar with that. We do that more often. We chose the bolted angle connection to the diaphragm on the second bridge. And because of it, and we decided to try that because in our shop, hole making is a little bit more automated than stiffener welding. And so we felt like we saved a little bit of time with the bolted connection. Then the only other fabrication operation that had to take place was to camber the beams to account for the dead load deflection so that the beam would properly conform to the roadway grade after the slab was poured. So for us, and I know we're running short on time, but for us, these were really simple and easy to fabricate beams, and we were able to compete with concrete. We as a steel industry did not win all 5, but we won 4 out of 5, and we, our company, DeLong's in particular, didn't win all 4 of those that went steel, but we won 2 of the 4. So the way I look at that from the owner's standpoint, if I'm the county of Franklin, if I'm the taxpayer in Franklin County, I look at this as a success because even though they paid the engineer to do 2 steel designs, on each of the 2 bridge designs on each of the 5 locations, they saved enough money in the material savings and the construction savings to more than offset the extra that they paid the engineer for his design time. Michael, that's all I have. We'll send it back to you.
All right, thank you. So I just want to finish up here. I just have a couple minutes. Just talk about the performance of today's short span steel bridges. Like Gary said, simple and practical details. That's where steel bridges have made the most impact in the last couple decades. And of course, since they're lighter bridges, you have lighter equipment to put them into place and smaller abutments. You can use smaller abutments. For speed of construction, accelerated bridge construction is becoming so important across the whole country that when we close down a road, that is a big inconvenience to the public, and we need to minimize that. And certainly steel has some advantages there because of the weight, because of the modularity, because of the ability to put it in place easily. Longevity, 100 years plus. There's thousands of 100-year plus bridges, steel bridges out there. That's because of durable materials and corrosion protection systems like Jeff talked about, integral abutments and getting rid of the deck joints, which we tend to do now with these bridges, really improves that. But if we talk about resiliency and sustainability, I have a slide on that. We want to be in the middle of this diagram. We want a resilient and sustainable steel bridge with 100+ years of service life. Now, on the left side, I have resiliency. And yes, steel has a lot of advantages there. It's inspectable and repairable, redundant systems, flexible, adaptable, resistance to natural and man-made hazards. And if it does get damaged or if it does corrode, we have fast restoration. But on the right side is that sustainability, which we talk about recyclability, where steel is America's #1 recycled material. Reduced material consumption, where steel has that high strength to weight ratio where we can optimize that. Energy efficiency for the construction, and recycled steel. And our mills are putting in new energy efficient furnaces and things like that, and using renewable energy sources. And then, of course, the bottom one, which everybody talks about, is greenhouse gas emissions. And those have been reduced because of the recycling and because of the energy efficient furnaces and because of the renewable energy. So where we feel that steel bridges really can make an impact in that middle section where they are resilient and sustainable, and we can just expect them to last well over 100 years. And so, summary and conclusions, what I would like to say is that we want that, well, I'm a bridge engineer. Today I'm a steel bridge engineer, but I'm a bridge engineer overall. And I want that competition between steel and concrete because that's healthy for cost, certainly, but also for quality of bridges, also for industry responsiveness, and also for industry capabilities. And that steel and concrete are competitive on first costs and life cycle costs, and steel or concrete may be the lowest cost for a particular project, and that we need to consider both for our individual projects. So if we go back to that data from Missouri, we looked at the 10 years from 09 to 18. Now let's look at 5 years from 21 to 25, where Missouri built 230 typical concrete bridges and 24 typical steel bridges, a big increase in steel bridges because they're competing them and because steel bridges compete well and win. And this doesn't even include those bridge bundling projects where 25 steel bridges were part of that farm project, and 24 and 12 and 4 are part of some of their other bridge bundling projects. And so this doesn't even include those, but we see that Missouri, because they compete, the number of steel bridges has gone up. But more important than that, that competition has been saving Missouri money. And with that, I will end with this slide again saying, hey, I encourage you to visit shortspansteelbridges.org, contact Dan Snyder, contact myself, contact anybody from the Alliance if you have questions or need help with a project.